All right, so I wanted to. Sometimes it's useful to describe vectors in one reference frame, like a rotating reference frame. However, rotating reference frames aren't inertial. So a lot of times we would like to be able to translate a vector described in a rotating reference frame in terms of the inertial reference frame, and that's so I'm using this depiction here to uh, set up the situation. All right, so what I have here is a set of so an inertial reference frame signified down here where I have like the I, J, and K vectors, so I, J, and K. And then what will wind up being a rotating reference frame, U, V, and W, are 3 unit vectors signifying another reference frame that will be eventually rotating about with an angular velocity of omega here. All right, and then A, this vector A, capital A, is rotating and is defined in terms of the rotating reference frame. All right, and see the motion of A. You might want to do this like say the motion of A is simplistic in this rotating reference frame, reference frame, but maybe complicated in terms of the inertial frame. So in this case, A is just simply rotating about the V axis, which uh, is a rotated form of the y-axis. All right. So if I set the angular velocity, so now the reference frame is rotating, and A, the motion of A, is quite complicated when it comes to describing it in the inertial reference frame, but still it's quite simple with regards to the rotating frame. So this is the situation that I'm going to derive mathematically here in a second. But let's see. Now, one thing I want to point out is that uh, at the initial and then during this derivation, the base vectors at this instant in time are aligned with the vectors that make up the inertial frame. And that we can always do that, right? I can always choose these to be aligned with the rotating frame. However, the idea is that the derivatives are non-zero in the rotating, or with the derivatives of the vectors with respect to the inertial frame are non-zero, and that's what we're going to get at here. So they are aligned yet in motion. Okay, that's the idea.
So sometimes, like I was saying, a vector is easier or more easily defined in terms of a reference frame that is rotating. Okay, it's just a thing that happens sometimes. So um, and then so what we're going to be dealing with here is not necessarily the translation or the rotation of the vector itself into the inertial frame. What we're going to be dealing with is the translation of the derivative in terms of the reference rotating frame into the inertial frame. Um, Hopefully it'll become clear in a second. So the animation was probably a little bit better at depicting this. But what I have here is a inertial frame, so I'm going to use capital letters to signify the inertial frame. Okay, and then I have there's a rotating frame given by the lowercase letters. So it's the z-axis and therefore the the k vector, k unit vector. And this is currently, these xyz axes and the capital XYZ axes are aligned currently. However, the lower ones aren't. The lowercase frame, the rotating frame, is rotating about this vector omega. And I'm interested in translating this vector A, or its derivatives, into the inertial frame. Okay, so the XYZ, this is the rotating frame. That's capital omega. And then the okay, so because they're aligned, at this instant, these things are true. The unit vectors are all equal to one another. As well as the components of the vector A are all equal to one another. It follows just by the fact that all the unit vectors are the same. So A at this instant, this is true only at this instant in time because of the fact that the two coordinate systems are aligned with one another. Okay. In the next instant, that'll cease to be true. Okay. So the vector, I'm going to use this notation. The vector A, as seen from the rotating reference frame XYZ, is equal to this is a little bit redundant, but it's just really just a restatement of this, but okay. So right now the two vectors, their coordinates are identical. Okay. Now so I can take the time derivative in the inertial frame, but I'm going to use these. The time derivative in the inertial frame, so I'm going to take the time derivative in the inertial frame but I'm going to use these vectors, or I'm going to use the components as explained, or from the rotating frame. So from the point of view of x, y, z, the inertial frame, the lowercase i, j, and k vectors are rotating. So this time derivative here is non-zero, right? Likewise, I had to apply the product rule here, and now I apply the product rule in the y direction. And then again in the all right. Now I'm going to take that same time derivative in the XYZ frame using the same basis vectors, the lowercase I, j, and k. So in this reference frame, I dot, j dot, and k dot are equal to 0. So we're taking this derivative with respect to the rotating frame. So from the point of view of the rotating frame, these vectors are stationary. The I, j, and k vectors are stationary, right? Because our point of view is rotating with those vectors about omega. So from our point of view, these things are not moving. So in this frame, these three vectors are 0. So that means that from the point of view of, we can rewrite this from the view of the inertial frame. That's just the derivative as expressed in the rotating frame, plus these terms associated with the changing basis vector. All right. So if we know what we're saying, know the vector A expressed in the lowercase xyz or the rotating frame, we have to, in order to get this derivative expressed in the inertial frame, we have to add these three terms here. Okay. Now, it's pretty straightforward to figure out what the time derivatives of these are. So they're rotating about omega. So what we have here is a vector omega. And just for instance, let's take the I vector. All right. So this is the I vector. And what's it going to do? It's going to trace, if this were a constant speed omega, it's going to trace a circle of, it's going to trace a circle around omega. according to the right-hand rule. So it's going to be rotating in this direction. So I dot at this instant is looking like this. Okay, so that's what's going to happen. Now omega may be changing in general, so it may not complete this circle. It may have a much more complicated path, but at this instant it is on this trajectory. All right, and so I dot is perpendicular to both I and omega, and in fact it has the magnitude and is given completely by and likewise for J and K. So it's just given by the cross product. For the rotating frame. From the point of view of the rotating frame. Oh, I'm sorry. From the point of view of the inertial frame. Okay. And so I'm just going to skip a step here, I think, maybe. Or maybe not. And, so we can distribute the components AX, AY, and AZ into that cross product. So here's the gist of it. Here's the upshot. So if I know the vector, and I'm able to easily calculate its derivative in terms of the rotating frame, I can find the components in terms of the components of the derivative in terms of the inertial frame by applying this additional correction here, which is just the rate, the angular velocity of the frame crossed with the vector itself. Now, as at this point, there's some ambiguity as to whether A is expressed in the rotating frame or the inertial frame, and it doesn't matter, because if you remember during the setup, the two are equal at this point. At this instant, the vector itself is the same in both frames. The components of the vector are the same in both frames. However, the derivatives won't be, because of the fact that even though they are currently aligned. In the next instant, they won't be.